Hi, we're at the San Leandro Costco. People from all over the East Bay come here to buy groceries, household items, electronics, tires, and of course, the famous cord hot dog. But we're here today to do some carpool chemistry. Today, we're going to take a look at the ideal gas equation. Let's say that it's a hot day and an amusement park balloon is filled with 44.3 grams of helium. The temperature is 37 degrees Celsius and the pressure is 1900 millimeters of mercury inside the balloon because it's being squeezed by the rubber balloon. The gas is being squeezed, that is. Calculate the volume of the balloon. What I like to do first of all, of course, is write down given. And let's list the items that are given to us. We're basically translating from the language of English here, these words, to the language of chemistry. As we can see, the first piece of information that's given to us is 44.3 grams of helium. Notice how we don't have to write down that's a hot day. We don't have to even write down that it's an amusement park. We just need to write down 44.3 grams of helium. The next piece of information that's given to us is the temperature is equal to 37 degrees Celsius. And the pressure, P, is equal to 1900 millimeters of mercury. The next item that you want to do is to write down the word find and the volume, which is V. And so we've learned that these parameters, temperature, pressure, volume, what equation comes to mind? The ideal gas equation. That is PV is equal to nRT, where P is pressure, V is for volume, N is for the number of moles, for circles, and T the temperature. Let's do a little checklist so we can see what we have available to us in PV is equal to nRT and what we still need to find. Do we have a value for pressure? Check. Do we have a value for volume? No, that's what we need to find. Do we have a value for N, the number of moles of this gas? Well, the answer is no, but do we have a clue that's going to help us to find the number of moles? Yes, we do. That clue is the fact that we have 44.3 grams of helium. So instead of putting an all-out check there, I'm going to put a half of a check there. I like to call it the EK. And then, do we have a value for R? The answer is yes. Just like the value for pi for a circle is 3.14, the value for R for gases is always 0.08221. Do we have a value for temperature? The answer is yes. Okay? What we need to do now, however, is to make sure that we're in the correct units. Let's take a look at P. Is the unit for pressure the correct unit that we need when using the ideal gas law? The answer is no. We need to put our pressure in terms of atmospheres. And so I like to do this right up here in the given and get it over with. Times 1 atmosphere for every 760 millimeters of mercury. And if we crunch that on our calculator, we have 1900 times 1 divided by 760 is equal to 2.5 atmospheres. Let's take a look at the value for R. We'll have that's a constant, so that comes with its own set of units. But how about temperature? Do we have our temperature value is 37 degrees Celsius, and the temperature unit that we do need to use when dealing with gases is Kelvin, so we need to add 273 is equal to, well, that's 37 plus 273 is equal to 310 degrees Kelvin. All right, and then let's take a look at one more thing, and the number of moles. Well, we don't know the number of moles, but we do know the number of grams, and so let's do it right over here. Let's convert from grams to moles for helium. And from our periodic table, the atomic mass of helium is 4.00 grams per mole, However, we need to make the grams cancel out, so we say that there's 1 mole for every 4.00 grams, and calculating that gives us, let's see, 44.3 times 1 divided by 4, and I see 11.08 moles of helium. So I think we're now ready to substitute these values into our equation. We're looking for V, stuck to it is P, so I think what we should do algebraically is divide both sides of the equation by P in order to get rid of the P from the left-hand side of the equation. That's nRT over P, and the P cancels out, and so now we have V is equal to nRT over P. We can now substitute our values in. For N we have 11.08 moles, and then our value for R, 0.0821 liters times atmospheres over mole degrees Kelvin. And then for T, our T in Kelvin is 10 degrees Kelvin, and all of that's divided by our pressure, which is 2.5 atmospheres. Now let's double check and cancel out our units. We cancel out moles, it cancels out with moles. Kelvin cancels out with Kelvin. Atmosphere we have in the numerator, atmospheres in the denominator. That cancels out, and we're left with a unit of liters. Is liter an appropriate unit for volume? The answer is yes. So there's a pretty darn good chance that we did this correctly and didn't get things flipped upside down. Let's go ahead now and do the calculation. 11.08 times 0.0821 times 310 divided by 2.5 equals 112.8, and the units there, of course, would be liters. So that's your answer, and that's how you use the ideal gas equation. From the San Leandro Costco, this is Carpool Chemistry. Thanks for watching.